Hi, welcome back to Physics 210. This video is about the solution of the tutorial 8. Okay, we look at our question number 1. This one is tutorial 8. Kinetic theory of gas and also gas law. Okay, we look at our question number 1. Question number 1 states that asks that A is primarily a mixture of nitrogen N2 and oxygen O2. Assume that each behave as ideal gas. Okay, so you already know the condition of the ideal gas. Determine the root mean square speed of nitrogen molecules when the temperature is 20 degrees Celsius. Okay, the formula for root mean square speed. Okay, the root mean square speed, RMS, the root mean square speed is the VRMS is the square root of 3kT over m. Okay, 3kT over m. So the value for K is a Boltzmann constant. This is the one, and the temperature is 20 degrees Celsius change to Kelvin, and the mass m is the mass of the nitrogen molecule. Okay, so we have 3 times 1.38 times 10 to the power minus 23, temperature 20 plus 273, and then divide by the mass 4.65, 10 to the power negative 26 kilogram. Okay, so answer will be, here we have 3 times 1.38 power negative 23, and then multiply this 20 plus 273. Okay, we'll make it more accurate, 0.15. Okay, alright, and then divide by the mass, this one, 26, and then don't forget the square root. So we have 511 meter per second. Imagine how fast will that be? Okay, very fast. Okay, that's question number 1. So the main thing here that you have to remember is the temperature must be in Kelvin, yeah? In absolute temperature. Okay, number 2, a CO2 tank, which is carbon dioxide tank, has a volume, okay, V 0.584 cubic meter. The mass of the tank before and after refill are 89.5 and 125. That means the difference is a mass of the CO2 gas. So I have 125 minus 89.5, and that will give us 125 minus 89.5, 35.5 kilogram. Okay, 35.5 kilogram. So there's a mass of the gas, volume, mass already have. And the temperature of the tank at that time, the temperature is 28.9 degrees Celsius. So you change to Kelvin, 28.9 plus 273.15, we have 302.15. Okay, sorry, 302.05 Kelvin. Alright, so list down all this information first before you start your calculation. And then what else? Okay, find the gas pressure of the tank. Our formula allow us to calculate the absolute pressure. Yeah. Okay, so the formula that we can use here is what? PV equal to nRT. Okay, PV equal to nRT. P pressure, V volume. We need to find the pressure first, and then the N is the number of mole. R is a gas constant, 8.315, and then the temperature is already given. Alright, and then why we are given the molecular mass? Because you need to change the mass into mole. Okay, but remember, you see, this is 44 gram per mole. Okay, and what you have here is kilogram. So we put down the formula first. Yeah, this is a mass of the gas in gram. This one is kilogram, and then divide by relative molecular mass, RT. Okay, now I can put in everything. Find the P first. That will be mRT over Vm. Okay, so the mass is 35.5 times 10 to the power 3, change to gram. The gas constant 314, temperature is 302.05, already calculated. And then our volume, 0.5 at 4, and the molecular mass is 44. Okay, gram per mole. Alright, so that is our pressure, 35.5 power 3 times 8.314 times 302.05 divided by 0.584 times 44. Okay, so that pressure is 3.469 megapascal. Okay, so we put it 3.47 10 to the power 6 pascal. Okay, pascal. But our gauge pressure, okay, our gauge pressure is our absolute pressure minus the atmospheric pressure. So what's our atmospheric pressure? Well, our atmospheric pressure is not given here. They should give you this atmospheric pressure is equal to 1.013 times 10 to the power 5 pascal. Okay, we minus that one. 1.013 10 to the power 5. Okay, we get this 3.37 10 to the power 6 pascal. Okay, that's our gauge pressure. Alright, okay, so that is the question number 2. Alright, we go to question number 3. Question 3, an expandable container contains this much oxygen, volume 1.0 10 to the power minus 2 cubic meter of oxygen. This one is oxygen O2 at a pressure P of 50 kilopascal and a temperature T of 20 degrees Celsius, which is equal to 293.15 Kelvin. Okay, 293.15 Kelvin. Alright, that's the initial condition. And then A, calculate the quantity of gas in mole. Quantity of gas in mole, A, N is equal to the mass divided by molecular mass. You see, molecular mass is given 16 gram. Okay, 16 gram per mole. So you need to find number of moles, so the mass of oxygen you have to find out first. Okay, here, or you can straight away use that, what we call that, because you don't know the mass, right? So we use ideal gas law. So we have PV is equal to nRT. We don't even need to know the mass of the oxygen, but later you're going to find the mass in B. Okay, so our N is equal to PV over RT. Okay, so now we can calculate our number of mole. P, pressure 50 kilopascal multiplied by volume 1.0 10 to the power minus 2, and then divide by the gas constant at 0.314 and temperature of 293.15. Okay, see what do we get? 50,000 times 1.0 minus 2, and then divide by 8.314 times 293.15. Okay, so we have 0.205 mole. Okay, and that is the number of mole of gas, oxygen gas. B, what is the mass of the gas in kilogram? Well, you know that mole is M over big M. So the mass, okay, is equal to number of moles 0.205 times molecular mass 16 gram per mole. So mole and mole cancel. You have this one multiplied by 16. You have 3.28 gram. Remember, okay. But the question one in kilogram, right? So you have 3.28 10 to the power negative 3 kilogram divided by 1000. Okay, so that is a B. C now. Okay, C, if the gas expands to a new volume, okay, new volume, so there is a V prime is equal to 1.5 10 to the power negative 2 cubic meter at constant temperature. So the T prime is the same as the T, which is 293.15 Kelvin, no changes. It's a constant temperature process, so this is an isothermal process. Now, what will be the new gas pressure? Okay, isothermal process is Boyle's law. Okay, so we have P1 V1 equal to P2 V2. Okay, you need to calculate P2, right? So your P2 is equal to P1 multiplied by V1 divided by V2. Okay, you have P1 original pressure is 50 kilopascal. You can actually give your answer in kilopascal as well, and then multiply by the volume V1, this one, 10 to the power negative 2, and then become 1.5 10 to the power negative 2. Okay, so the changes is just cancel these two, so just divide this one by 1.5. Okay, so pressure should be reducing because the gas expand. So we have 50 kilopascal divided by 1.5, so we have 33.3 or 33 kilopascal. Okay, 33 kilopascal. Alright, so next time use your logic, common sense. When using this type of common sense, is much easier to check whether you really have a correct answer or not. At least common sense tell you that whether your answer is in the correct range or not. Okay, next question 4. This is our page 1. Yeah? Okay. Okay, question 4. Question 4. Sorry. So Guy-Louzet's law 4. Okay. So Guy-Louzet's law, okay, states that, what is Guy-Louzet talk about? Pressure and temperature, right? That the absolute pressure of a gas in a container, okay, no need the word container, the absolute pressure of a gas is, okay, is directly proportional to the absolute temperature, okay, of the gas, okay, of the gas, with assumption, okay, with assumption that two things here. Okay, what is the assumption? Number one, mass must be constant. Okay, that the mass, and one more thing, because this one is between pressure and temperature, right? So the volume must be constant. Okay, assuming that, with assumption that the mass and volume, okay, the mass and volume of the gas are constant. All right. So in equation wise, we have pressure directly proportional to temperature in Kelvin, Pascal. So we have this one over T is equal to a constant K. So since it's equal to constant K, we have a stat 1, stat 2, we have P1 over T1 equal to P2 over T2. Alright, so not only two conditions, you can continue with P3, T3 and so on. So that is our answer for the Guy-Louzet's law. Okay, not gay. Yeah? Okay, next we go to question number 5. Quite the same thing here. Page 2. Okay, question 5 asks for state the ideal gas law. Okay, ideal gas law. Okay, ideal gas law states that, okay, the absolute pressure of a gas is directly proportional to the absolute temperature of the gas and the number of mole of the gas. Okay, and also inversely proportional to the volume of the gas. Alright, okay, so if we write down in formula, is P directly proportional to what? First absolute temperature and then number of mole, right? So you have N and T. And then inversely proportional to the volume V. So we put a constant in front, but this constant is has a special symbol, it's R. So NT over V. So you write it down, we have PV equal to nRT. This one sounds looks more familiar than this one, right? Okay, so that is our ideal gas law definition. Okay, next, question 6. Okay, question 6. A gas container contains 8 kg of oxygen gas at a pressure of 3 atmospheric pressure. We have a mass is equal to 8.0 kg at a pressure P of 3.0 atmospheric pressure. The oxygen gas is then replaced with, this one have two conditions. The oxygen condition here, this is for O2. After that, the mass is different, become 10 kg of nitrogen gas, while the temperature is kept constant. So the temperature are constant. Calculate pressure exerted. Okay, this one unknown. Okay, so this one I'll call PO, this is PN, this is MO, this is MN. Okay, this one unknown. Need to calculate this. Volume the same. Okay, volume is the same because it's the same container. Okay, it's the same container, so volume is the same. So you write equation now. Okay, for oxygen, PV is equal to nRT. So this one is pressure of oxygen, number of mole of oxygen. The rest are the same. So we have equation 1. And then for nitrogen gas, we have PN. We have PNV is equal to NNRT, equation 2. So it's very easy to observe now. To get the Pn, you divide the equation so that V gone, R gone, T is gone. Okay, so 2 divided by 1, you have Pn over Po is equal to Nn over N naught. Okay, now what else? We have the mass, right? Okay, mass, later I need to find that value. So I need to find this. Pn is equal to P naught. And this one will be, okay, never mind, we write down first. N and N naught. So this one here, okay, oxygen is 3 atmosphere. I think the question didn't say the how many atmosphere, right? How many, what is the unit, right? So we can leave the answer in atmospheric pressure. Atmosphere, okay, atmosphere. P is 3 atmosphere. Remember, or you've been write down so that you don't write down Pascal later. Okay, and then here, number of mole of nitrogen is equal to the mass of nitrogen. Okay, the mass of nitrogen, which is 10 divided by the molecular mass. Molecular mass given for nitrogen is 14. Okay, 14. Wait, I'm not very sure here. Let me check first here. Check again for some other one. Oxygen 16. This is a relative atomic mass. Sorry, I think I have done some mistake already. This is atomic mass. So for molecule should be 32. If this is a relative molecular mass, then it should be 32 gram per mole. Okay, so before we proceed to more error, I will check first. This one correct already because this is molecule. Okay, I need to go back to question number 3. Sorry guys, go back to question number 3 to check on my calculation here. Question 3 here. Oh, okay, there's a where's the error here? The error should be this one. Then the error should be here. This one should be, because this one talking about oxygen gas, right? Oxygen gas, it should be 32 here. Sorry guys, this is 32. Okay, let's check again. 0.205 times 32. Okay, so it's 6.56 gram. So 6.56 times 10 to the power negative 3 kilogram. Okay, double that one. Okay, double that one. So here no changes. Okay, luckily this one no changes. Okay guys, remember question 3 supposed to be 32 here. Okay, 32 gram. Okay, but more because refer to molecular mass, it's not atomic mass. Yeah. Okay, and then now this question number 6 just now. You have to remember, yeah, the one given to you here, this one is atomic mass. So for O2 is 32, for N2 is 28. Be careful with that. So I hope in the exam question they will specify that clearly. Okay, but before that I will look at the question first before you look at it. Okay, now the nitrogen is divided by 28, but remember this is gram, right? So this one have to change to gram. 10. Okay, like that. This one for nitrogen, and then divide by the one for oxygen, 8,000 gram, divide by 32. Okay, alright, so that will be the one. Okay, here you have 10,000. Okay, divide by 28. Okay, and then divide by this one, 8,000 divide by 32. Okay, this is what we get here, and then we multiply by 3. Okay, so we have 4.3 atmosphere. Okay, 4.3 atmosphere. Okay, so when your molecule becomes smaller, okay, your molecule becomes smaller, the gas pressure will increase. You know why? Because you remember the root mean square for the pressure. Okay, your root mean square speed. When your mass becomes smaller, your root mean square speed increase. When your root mean square speed increase, your pressure will increase, and that's why it's very dangerous. If you have a container, for example, the one used to store CO2, and then you think like, well, it's just a tank, I maybe can use it to store some other gases, like especially like the one that is combustible, very dangerous, hydrogen. Hydrogen is like 22 times less massive, so that means the root mean square will be square root of 22 times more. It will definitely going to increase the pressure of the same tank. Okay, so when temperature increase to a certain value, it might explode. Okay, so that's why you study, okay, to know all these things, so that when you next time become engineer or scientist, when you do some conversion of equipment, or when you started to modify equipment, or you want to invent equipment, all these come into consideration. Safety is number 1. Okay, next question, number 7. Okay, so number 7 is state 2 assumption used in the kinetic theory of gas. I gave you 4 last time. Okay, we look at first one. A, the number of gas particle, okay, must be large enough. Okay, why? Okay, so that it is statistically viable. Okay, so that it is, or the system is, okay, so that the system is statistically statistically viable. That means your formula can be used to predict that one within a certain error. Okay, within a certain error, accepted error, I mean. Okay, that's number 1. Number 2, well, you can use the easiest one, the easier one. The collision, okay, the collisions between gas particles are elastic. Okay, elastic, right? And then maybe you can add in the other 2. Okay, we'll check on the other 2. Okay, next one, number 8. Number 8, the temperature of ideal gas is 45. Okay, degrees Celsius change to Kelvin 0.15. So you have 318.15 Kelvin. Okay, that is our temperature. Next one. What's the next thing given? Determine the average kinetic energy of the molecule of this ideal gas. Well, I have to tell you that the average kinetic energy is only calculable, is only depending on temperature. That's why you see you are given only this one, right? Okay, average kinetic energy, what's the formula? The average kinetic energy symbol is K bar, and we know that it is actually given by this formula, right? Mean square speed, and the formula is 3/2 kT. So see, this is a constant and this one multiply. Okay, at the moment you don't worry much about the 3 here. The 3 here, because we assume that you are studying gas particle. They are like monoatomic. Even though the previous one we assume the molecule as just use the same formula to calculate. Okay, so our average kinetic energy is 3/2 times Boltzmann constant minus 23, and then temperature 318.15 Kelvin. Alright, okay, we have this already, times 1.38 power negative 23, and then times 3 divided by 2, right? 6.59 10 to the power negative 21 joule. Okay, very small, right? But the accumulative effect of a lot of gas particle is gigantic. Next, number 9, a smoke particle with a mass, okay, of 3.0 10 to the power negative 16 kilogram move with Brownian motion. This is Brownian motion everywhere you go, random, in air at 27 degrees Celsius. Okay, 27 degrees Celsius, that will be 300.15 Kelvin. Okay, just check, plus 27, 300.15, and then calculate the root mean square speed. Okay, root mean square speed formula is 3 kT over m. All given. Temperature already, this one you already know, so okay, we put in the value 1.38 minus 23, and then multiply by temperature 15, this one, and then mass. Okay, the mass is 3.0 minus 16. In this type of calculation, always remember the square root. So we do the one inside first. 3 times 1.38 power negative 23, okay, Boltzmann constant, and then times 300.15. Okay, done. Divide by 3 power negative 16. Get this square root, don't forget that. Never done any mistake. Why the value are so small? Oh, root mean square speed. Let's see what we have. 3 kT mass. Oh, this mass is huge. What type of gas is this? 27. Okay, 27, 3 kT over m. We have the same formula before, right? 3 kT over m. Okay, so the mass is extremely small. I wonder what type of gas is this. Okay, anyway, our answer is this: 6.44 10 to the power negative 3 meter per second, and this one is about 6.44 millimeter per second. This must be a gigantic gas. Okay, gigantic gas, very large. Okay, very large. I'm not sure whether we have this type of gas or not. Okay, even kentut is faster than this, right? Okay, check again. 3 times 1.38 power negative 26. Okay, and then times 300.15, 3 kT. Okay, we get this, and then divide by 3 power negative 16, right? Okay, this one, and then square root of this one give, different again. Okay, let's check again. 3 times 1.38 power negative 23 times 300.15. Okay, and then divide by 3 power negative 16. Okay, and then square root 6. This one just now I typed wrongly. Okay, that is the answer for this. Okay, so done for our tutorial number 8. After this, give tutorial number 9. That is your last tutorial. Okay, so see you again.